All right, we're cooking. So last time we were talking about um, memory, I'm told, right? And Abe, you were telling us how more memory is good, right?
Sure.
Okay, and we talked about servers and servers. What's the difference between servers and servers?
One server, the other server.
What was the difference between hardware servers and software servers that we talked about last time? We used the example of the Big Mac Pro we have down the hall. We could call that a hardware server. What is a hardware server? If we were to give a concise definition of that, probably a beefy computer with lots of processors, lots of memory, capable of doing lots of things. Why would we want one of those? Do we always just go out and buy the fastest, latest, greatest, coolest computer because it has the most RAMage, the most hard driveage, most fastest graphicsage? Because it's cool, bragging rights, right? Okay? But most of our computers that we have on our desktops are single-user computers. The only person they have to please is us. Okay? When we would deal with a piece of server hardware, some, potentially not necessarily big, but powerful, lots of RAM, lots of processors, how many people does something like that need to, quote, please? Many. If you think about Google's web server, not only is it a piece of software, but they have a, beefy computer. Actually, they have a computer cluster with load balancing, so they probably have 200 beefy computers. How many people does that server, let's just call that one monster piece of hardware, how many people does that need to please on a per second basis? A lot, right? How many Google searches are happening every single second? A lot. So it's solving a completely different problem. That's where we start thinking about the advantage of having multiple cores, the ability to do more than one thing at once. The idea of having a lot of RAM, because all these different requests are going to have variables associated with them, right? Every single time you go to google.com, you type something into the box and hit search, that's getting set somewhere, and that search string needs to get stored somewhere. And then behind the scenes, Google's magical algorithm that goes and figures out what you're looking for is going to also create a whole bunch of variables, right, associated with your search. And so let's just say there's 30 variables associated with every search that need to be stored in memory. And why are variables stored in memory rather than hard drives?
Memory's fast.
Memory's fast. So memory's for short-term storage, hard drives are for long-term storage, right? So we're going to store it in memory because we want it to be really, really fast. All right, so let's just say there's 30 variables associated with every single Google search. And let's just say there's 1,000 Google searches per second, which I'm sure is a huge underestimate, right? Okay, so now we have 30,000 variables that need to be stored on a every second basis. Will having a lot of memory benefit us? Yeah, so that's where we're going to start utilizing all that memory. If we're sitting there with a single computer, and we'll pick on Dave since he skipped class today, with his, what is he? Does he have 32 gigs of RAM in his laptop?
Yeah.
Okay, so we got a guy with 32 gigabytes of RAM in his laptop. He's a single user. Is he ever going to use 32 gigs of RAM in his laptop as a single user? It would be an interesting experiment to have him try to do that. Try to use 32 gigabytes of RAM as a single user.
But not just have it assigned to virtual machine.
Even then, I think you'd be hard pressed as a single user to use that RAM. You couldn't do it you'd have to do it with a C++ program or a C program and just write an infinite loop that just kept creating memory. Then you could pull it off pretty quickly. Probably a 2 or 3 second program could just run you out of memory. But in Java, you're running in a virtual machine, so you're going to be protected, right? Java is going to give you an out of memory, out of stack space exception way before anything bad has actually happened. So that's why we need these hardware servers. Now, what about software servers? What's the difference? What's a software server? Well, by definition, the word server says it serves something, right? And last time we talked about Google's web server, which by default runs on port 80. Remember we were doing the crap in the web browser, and then I opened up the telnet session, and we actually connected to it and saw some HTML-y looking stuff. So that's a piece of software that's running on probably what we would consider a piece of server hardware. But that single piece of software is listening on port 80 on that hardware and is serving requests. And a single piece of server hardware, or even what we might consider non-server hardware, for instance, any of our laptops, we could run a web server on our laptop. You can go out to, if you're running Windows, you can install IIS, Internet Information Server, and host web pages right on your laptop. You'd be able to access them locally, certainly. You might be able to access them on your local network, depending on what kind of firewalls were set up. But you can certainly run a server on there, so you don't need server hardware to run server software. Typically, server hardware is going to run more than one piece of server software, unless you're probably Google's web server, where you have plenty of users for your single server software web server across your vast amount of server hardware. Like, I'm very certain that the Gmail application, that server, their mail server, is running on different hardware than their web server is running on. But that's because of the nature of Google. Lots and lots of requests. Concordia, could we have our mail and our web server running on the same computer potentially? At least it seems like a significantly more reasonable thing, right? Okay, so server software is a piece of software that listens to a network port and serves data. Server hardware is just a really cool looking computer with a lot of cool hardware in it that we hopefully will take advantage of in a server setting. Okay, there is a distinct difference, yet we typically use the word server interchangeably, right? Okay. So we have something called DMA, direct memory access structure. You've probably seen that if you've ever bought RAM for your computer. Usually gives you a gigahertz rating in term for the DMA side of it. It's the memory bus, how you're communicating with RAM. And sometimes we have external devices that try to communicate with RAM at the same speed. These would typically be, if any of you have looked at internship opportunities, kind of a big thing today is storage area networks. SANs, S-A-N. And these guys have communication channels between each other that all connect to a single central server, piece of server hardware, and that communication channel needs to be very, very, very quick. Okay? So DMA, we can kind of throw it as a throw-out term, but that's kind of what those things are talking about. All right, so let's talk about the difference between different kinds of memory. Talked about it a little bit last time, like you just told me a few minutes ago, that memory, we use memory for our variables because it's fast. We don't use hard drive for our variables because it's slow. Are all hard drives created equal? Is a hard drive a hard drive a hard drive? So if you have your hard drive go bad in your laptop, let's say, and you're going to go on to newegg.com, you're going to order a new hard drive. What are some things you're going to take into consideration? Go ahead. Okay, so a 2.5-inch drive rather than a 3.5-inch drive. You know, wouldn't that be funny? You order the 3.5-inch physical drive that's made for desktop computers, and you get it, and that thing's not going to fit in your laptop, right? It probably weighs as much as your laptop. All right, so certainly make sure you're going to get the compatible hard drive size. We really only have two. 2.5-inch is your laptop drives, 3.5-inch is your desktop drives. You mentioned RPM. Okay, RPM speeds. What does that mean? RPMs. Okay, is more RPMs better than less RPMs? Sort of? What do you mean sort of?
The hard drive has a set amount of data that it can move at once, if I'm remembering correctly. So if your hard drive can spin really fast, but it can't move all that much memory at once, or move all that much data at once, then it might be slower than a hard drive that maybe spins slower, but can move more data at once.
Okay. When a hard drive spins, we talk about that, that benefits us in a very specific way when we deal with how we use our hard drives. So the faster your hard drive spins, that equates to faster access times. When we search for a file, we're looking for some file on our hard drive, and then we need to access that file. The faster that hard drive spins, the quicker we can access that file. Now, why is that beneficial? I mean, so what are some different RPM speeds we might be aware of with hard drives? What are the ones you've heard of? 7,200 RPM. Next. How many of you built your own computers in here again? How many of you looked at the hard drive specs when you were buying it? Okay, give me some more RPMs. 10,000 RPMs. Okay, keep going. Why don't we go to the ones below 7,200? 5,400. We'll just pretend like you said that. Okay, 5,400 RPMs. Broken hard drive. What about 4,200 RPMs? Any of you have a 4,200 RPM hard drive? You typically would find those in laptops, kind of low-powered laptops. Now, what do you think the difference in access time is going to be between a 4,200 RPM hard drive and a 7,200 RPM hard drive? That's our real range. There does exist 10,000 RPM hard drives, and for those of you who, any of you have a 10,000 RPM hard drive? So none of you people who built a gaming monster put a 10,000 RPM hard drive in there? Instead, you just put a $2,000 graphics card and a $900 processor? A $10,000 RPM hard drive would have helped you more than the processor. Okay, so 7,200 RPMs is and 5,400 RPMs tend to be our two toggle points, right? So even we just use that. In a desktop computer, what do you think the perceived speed difference will be between a 5,400 RPM hard drive and a 7,200 RPM hard drive? You don't think you'd notice a difference? Where would you notice the difference? If I said you would, where do you think you would? Okay, possibly opening applications because we have to search for it and then access that. Now we have to load it into memory. Okay, whether we're dealing with a 5,400 RPM hard drive or a 7,200 RPM hard drive, our modern drives are probably running serial ATA2, which are 6 gigabit per second. So they both are running the same bandwidth speed. So they can transfer data, we're going to call it at the same speed. Just one of them gets to the data a little quicker than the other one, right? Okay, so maybe launching applications, initially launching the application, there's going to be a little bit bigger delay with the 5,400 RPM than the 7,200 RPM. Now, what do you think that delay is going to actually be? We talking 5 seconds, or are we talking a fraction of a second? Okay, or maybe a second, a noticeable second. But we're not talking about a big delay. It's not going to be like you double click on Microsoft Word and it launches in instantaneously on one and it takes 40 seconds on the other. That's going to be close. But the 7,200 RPM drive is going to have a perception of being a little snappier, right? Is that better? Is it good to spend more money on that? What's the downside of more RPMs? Good.
Failure rate, like if it gets knocked or something, you get like scratched easier.
I suppose if the drive is running at full speed and you drop your laptop, there probably is some sort of technical way of arguing that a 7,200 RPM drive at full speed is more susceptible to damage than a 5,400 RPM. Not really what I was looking for. It's probably a true statement. Heat. Faster it spins, the more heat it's given off. And heat is bad for computers, right? Any of you laptop users ever get burns on your thighs? Evan, I don't want to know about your thigh burns. Those things give off a lot of heat, right? Okay, well, does that mean we don't get 7,200 RPM hard drives? Probably can get those, not a big deal. How many of you have ever seen a 10,000 RPM hard drive? The physical drive. They look different than 54 and 7,200 RPM drives. They have heat sinks on them. Just like when you got your high-powered gaming RAM for your machine. It wasn't just a stick of memory, right? It had some metal crap around it for venting the crazy heat coming off the high-powered RAM, didn't it? It did, didn't it? It looks cool, doesn't it? All right, so, the really high RPM hard drives tend to have heat sinks on them to dissipate heat. And then inside your case and your computer, you're going to have a fan and all that other crap to kind of move the air over that so it's dissipating heat and then moving heat away from it. All right, so if a 7200 RPM hard drive gives off a little bit more heat, we're going to call that a bad thing. And it's only a little bit faster when we talk about loading an application. Why would we spend our money on it? Because it is more expensive. You take the same capacity hard drive at 5400 RPMs versus 7200 RPMs, you're probably talking for a 1 terabyte drive, it might be a $20 swing. Might be the difference between $120 and $140. And that's a pizza and a half. So why would you get the 7200 RPM hard drive? Where else would you notice it? You mentioned launching applications. We only do that so often, right? A lot of us, we leave the applications open on our computer. Especially those of you with laptops. You have your email open, right? When was the last time you actually opened your email? Or did you open it 3 weeks ago and the application is now just perpetually open until the next time you reboot your machine? That's more common, right? Why close it? I need to check my email, might as well leave it open. So every 3 weeks we're going to notice that 1 second speed difference. That's worth $20, right? Maybe it is. But that's $20 you could spend on extra fans and liquid cooling. And more graphics stuff. So why the faster hard drives? Where else are we going to notice it? Go ahead.
Like booting up your computer.
Okay, booting up the computer.
Like from a cold boot.
Probably. Your machine will probably boot more quickly. That would be more than a 1 second difference. You might notice like a 5 or 7 second difference. How often do we do a full restart of our computer? Whenever our laptop crashes when we open the lid, right? We open the lid and things just don't seem right. Or we do a software update. That's when we restart our computers. The rest of the time the computer is perpetually on. It goes into that sleep mode thing, right? How does sleep mode work? Is it magic?
It is.
Probably invented by Apple, right? Sleep mode uses virtual memory. Takes everything that's in real RAM, real memory, the fast stuff, loads it onto your hard drive, which is slow, but the advantage is hard drives can store stuff long term. So the next time you open up your laptop lid, it can take everything that used to be in real RAM and load it back into real RAM. Now you're back up right where you left off. Because as soon as you turn off the power, as soon as you shut your laptop lid and all the lights go off, so you're not burning battery life, your memory is no longer capable of holding data. Memory has to have a constant electrical current going through it in order for it to remember crap. You get a little hiccup in that and it starts forgetting variables. Not good. Okay, so that's how that works. So you can maybe even argue that having that when you go from sleep mode back to a full up and running operating system, having the little bit faster hard drive from an RPM perspective may also be beneficial. Couple of seconds, something like that. Go ahead.
Do you think that hard drives ever get fast enough where we don't need memory?
Well, it's a good question, and we're going to talk about that, I think, here in a couple of slides when we talk about the hierarchy of speeds of things. I would say the short answer is no. Because we'll think about the nature of human beings. We always want things to be faster, right? So if hard drives get to the point of that speed, where do you think memory is going to go? Even faster, correct? So chances, maybe the better way to ask the question, or the better way to answer the question might be, will hard drives ever get as fast as memory is today? Possibly. That's possible, especially as we start moving into the solid state drives. I still think it's probably unlikely in its current form factor. We'd have to move to a whole new technology, I think, beyond solid state. I think maybe now we're talking about quantum computing and things like that. But I guess in the big scheme of things, it is possible that we might get a hard drive that is as fast as our modern day RAM. But I think when that happens, RAM will be even faster, or the equivalent of it. Whatever we're using for fast short-term storage will be even faster. So where are we going to really, really notice the benefit of that 7,200 RPM? When do we use our hard drives? It's kind of one of those things that's just always there. We know we need it. But when do we actually use it? When is your operating system actually working with the hard drive? Do you think it's rarely, sometimes, or all the time? Probably closer to all the time. What kinds of things does the operating system use the hard drive for? When you're writing your paper in Microsoft Word and you hit save, we're clearly using the hard drive then, correct? Saving it to RAM and then also duplicating it on disk in case you close the application. Saving means actually save it. Until then, what is it doing? It's making the updates in RAM, but RAM is not the same as it is in the hard drive at that point in time. When you first open a file, the file in its current state loads into random access memory, RAM. And then you're editing the file in RAM until you hit save. And only at that point in time does the hard drive, long-term memory, become a duplicate of what was in RAM, overwriting the old version. So that's one situation where we're using our hard drives, when we physically hit save. How often is that? Not that often. Most of our word processors today have some backup stuff in it, right? Where they do some saving for us in the background, just in case we're stupid and don't save for a week. Do you want to restore from the most recent backup when the Microsoft Word crashes unexpectedly when you haven't hit save in 3 hours? So it's saving like every 10 minutes or something like that for you. Auto-magically in like a temporary storage location, not overwriting your file on the hard drive. Do you think that's the only time that we're using our hard drives?
Is it virtual memory?
Okay, certainly virtual memory. When we're swapping stuff in and out of fake memory on the hard drive into real memory, how often is that going to happen? Depends how many programs we have open, right? But somewhat often. Does our computer do any logging? Is it keeping track of errors and what different applications are doing? Logging happens at the application level, so Microsoft Word probably has its own logs. At time X, person saved, click this button was clicked, this error occurred, it was caught, blah, 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 all sorts of error logging, right? Do you think the operating system has its own level of that?
Oh, sure.
Probably a lot. Whenever you have a problem with the operating system, it gives you the big screen with all the little weird numbers on it and crap. It says, do you want to send this report to Apple or do you just want to send this report to Microsoft? That's being logged somewhere. It's being written to disk. What else? How many of you have ever started a download in the background and then went off and done something else on your computer? Is that constantly writing to disk? How many of you have ever copied a large file from one place to another on your computer? And it goes at a certain speed. And then what if you start copying another file? What happens to the original one? Slows way down. Have you ever noticed that it takes a lot less time to copy 1 gigabyte, a 1 gigabyte single file, than it takes to copy 1 gigabyte of a directory with a bunch of files in it? Why is that? Still moving 1 gigabyte, right? Shouldn't 1 gigabyte take the same amount of time as 1 gigabyte? If you have a directory with a gigabyte of MP3s in it, music, or a single file. Maybe it's a Linux ISO or something like that, or more than likely it's probably your favorite current movie that's in the theaters that you downloaded illegally. It's about a 1 gigabyte file, right? It was a bad cam. You didn't realize it was in Portuguese. So we're moving 1 gigabyte either way, but in one situation, we have a directory filled with 200 MP3s. And in another directory, we just have a single file that's 1 gigabyte. That single 1 gigabyte file will transfer far more quickly than the 200 files that all add up to 1 gigabyte. Why? Go ahead.
Because the 200 files may be saved on different places on the disk. The disk has to go back and forth.
Probably are. Our file system on our hard drive works a lot like linked lists. What's the advantage of linked lists over arrays? Back to our programming world. We talk about linked lists. What's the advantage of those? Go ahead.
They're not contiguous in memory. You can have them wherever you want.
Okay, why is that an advantage? That's a fact about them. Why is that an advantage?
Because you can add more to them instead of just having a finite amount, specifying a finite amount.
Okay.
And also that you only need a smaller portion of memory to be able to hold it instead of having an array where it needs that much in a single spot.
Okay, so if we think about storing stuff on our hard drive, and let's just say the simple version of this is we just keep putting stuff one after another. So we're saving into a certain directory 50 MP3s, and maybe, just maybe, the moon's aligned and all 50 of those MP3s are right next to each other. Okay? Then a couple weeks go by, we used our computers for a bunch of different stuff, we saved stuff, blah, blah, blah. So there's some other things in there. And then we download some more MP3s. Then the YouTube, the free YouTube album came out, and you want to rip it to MP3 because you want to be able to listen to it without the cloud, right? So now you want to put that in that same directory. Well, the directory structure has a bunch of pointers in it. They're going to point to real places in the hard drive. So even though they live in the same directory, those next 20 MP3s are likely going to live in different sectors of the hard drive, different places in the hard drive. Even though this MP3 comes right after this MP3, in between, they're not even in the same neighborhood. So when you're copying that 1 gigabyte of MP3s, your hard drive is constantly having to seek between the different locations on your hard drive. Finished copying this file, now I need to over to this one, start copying that one. Now I need to over to this one, start copying that one. So we can see why that would be slower, right? Because between every single one of those 200 MP3s, we're having to do a seek. And find a single seek doesn't take all that long. When you add up 200 seeks, that's a lot of time. That's why it's noticeably slower. What else are we using our hard drive? I used the example a few minutes ago when, let's say you're copying, let's just say we have two 1 gigabyte single files. And we start copying one of them, and then we start copying another one. The speed of the original copy goes way, 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 way down. Why?
It's swapping between the two copies.
Oh, it's swapping between the two. Your operating system is trying to be a good operating system. Like, we want our end user to be happy, so we're going to make it seem like we're doing everything at the same time. Now, when our CPU is doing that, when it's doing a little bit of work over here, and a little bit of work over here, and a little bit of work over here, and a little bit of work over here, the CPU can move between those things really, really, really quickly, so we don't necessarily notice. Okay, so our CPU is like a race car. And our hard drive is kind of like me on foot. It's actually probably not even that close. So when we tell our hard drive to work a little bit here and then run over here and work a little bit here, then run back over here and work a little bit here, then run back over here and work a little bit here, we're going to notice that delay, won't we? Because how long is it going to copy one file versus the other? We're going to talk in this course about how those algorithms work. How do we decide? But some amount of time, right? So maybe we decide that we're going to work on each file for 2 seconds. Just throwing a number out there. So we're going to copy for 2 seconds here, then copy for 2 seconds here, then copy for 2 seconds here, then copy for 2 seconds here. That seek time between the two might have taken 1 second. Just saying. It'll probably take less than 1 second, but just using simple numbers. So now the amount of time it took to copy those files is more than twice the amount of time it would have taken to copy them individually, because of all the running back and forth it has to do in the middle. So why doesn't your operating system know that, oh, you're copying this file, let's just do this one first and get it done before we go and do this one? That would make real sense. That would make sense in real life. Let's say you're going to go vacuum out your car at the gas station. So maybe you're in your driveway and you're going to clean out your car first, get the big pieces of debris out, right? And then you're going to go over to the gas station and vacuum out the small stuff. We don't just clean out the front seat, then take the car over to the gas station and vacuum out the front seat, then drive back home, clean out the passenger seat in the front, then drive back to the gas station and vacuum out that. That would make no sense. Yet that's what our computer's doing when you're copying those two files. Why isn't it smarter than that? Why does it work that way? Is the human version of fairness or logic always the same as the computer's version of logic? Because computers can do stuff faster. It might take us 10 minutes each direction to drive to the gas station. But we're talking about 1 or 2 seconds for the computer to go between those two. Now, in the example we've presented, we say, that's not smart, right? That's dumb. What if you have 2 different applications? What if you have Microsoft Word and you're working on your paper, and you're also downloading your, the cam of some movie that just came out? Perfectly legally. I'm sure you guys know somebody who's in the industry. What if you couldn't save your Word document until that file finished downloading? Remember, you're on Concordia's network, so chances are you're getting this at 40 bits per hour. It's like, well, it's just an inconvenience. I can't save my paper for 2.5 weeks because of how long this illegal movie is going to take to download. Is that acceptable? Or do we want our paper to save like that? We want it to be instant. So we have a tough job now. The file system manager, the dude that's in charge of responding to I/O requests related to the hard drive from our processor, he's got a tough job. He needs to know what's going to make you happy at all times. It's like, oh, you want to save your paper? Well, I got this other job over here, and you're going to have to wait in line. That's not acceptable, right? Yet, when you're copying these 2 files, you want them to copy as efficiently as possible. You'd prefer it just finish one and then the other, and not be sprinting back and forth during but how can the computer tell the difference? How does it know that one task you're willing to wait for and another task you're not? Computers are dumb. What else might be happening on your computer when you're copying those 2 files? Might you also be working on your paper and hitting save? Not that any of you actually do your homework. We might want to do that, right? So we have to hit that lowest common denominator. The file system has to try to do everything at the same time. Mechanical hard drives aren't going to be great at that. And we're going to see major, major, major delays. How many of you have heard that solid state drives are faster than mechanical hard drives? That's like the buzz thing, right? Everybody wants to get a SSD drive, a solid state drive. Why? Oh, because it's twice the cost. It must be most bestest. Right? And they've even come down in price. You also can't get the capacity, right? You can go get a 3 terabyte mechanical drive for $120 or $160, whatever. Or you can get a 1 terabyte solid state drive for what? More, a lot more, right? And they've come way down in price. They were like $2,000 like last year. So let me get this straight. A third the capacity for 6 times the cost. And we're calling that cheap because the price of solid state drives have really come down. Is that worth it? How many of you have heard of fusion or hybrid drives? How do they work? What is a fusion or a hybrid drive? Just a cool name that we pay a premium for, right? It's like, well, I'd like to have a hard drive that's called Fusion. It's got to be worth $30. Any of you have a hybrid or a Fusion drive in your machine? He probably does. He just won't admit to it. It's like, I don't know what it does. No Fusion drive?
I think I have a.
You have a hybrid? You just think.
I'm pretty sure.
Okay, but you know what it does. Just was cool and a little bit more expensive than the previous one, so it must be better.
No, it's just what came with the machine.
I thought you built your own machine.
Oh. No.
Oh, you're talking about your laptop.
Yeah.
I got you. So what is a fusion or a hybrid drive? We're technologists. We should know this stuff. We don't want to get taken advantage of at Best Buy. It's a hard drive with 2 components in it. One of the parts is a solid state drive. The other part is a mechanical drive. What's the advantage of each? We already know the disadvantage. Solid state's expensive. So if we can get a drive that has a big chunk of mechanical and a littler chunk of solid state, so we only have to pay the premium for the solid state portion, that might be something we're interested in, right? What's good about solid state? What's the advantage of solid state that's outside the disadvantage of the price? We have this perception that it's fast, right? Anything else? Go ahead.
It doesn't have any moving parts, so if you drop it, it's less likely to break.
Did you copy off him?
I said first. You copied me.
Did you copy off him? So no moving parts. No moving parts probably means less heat, maybe less mechanical failure, well, because there is no mechanics to it, right? Does that mean that a solid state drive can never wear out? They just last forever?
They're perpetual.
Like, well, I never need to get a new one of these. Like, this solid state drive's been in this computer for 6 generations. You pass it down in the family. How do solid state drives wear out? Storing stuff on a solid state drive still has there's a residual. Think of it like writing something in pencil and erasing it. Then writing something in pencil and erasing it. Now you can get millions and millions and millions and millions of writes and erases, but eventually the medium that you're writing to does wear down. Okay, so a solid state drive is not perpetual, but it does have a longer life than a mechanical drive. Chances are you'll replace the drive because it isn't a big enough capacity before the drive will actually wear out because of mechanical failure from the medium itself. Now that doesn't mean you won't have electronic failure. You know, all sorts of stuff can go wrong between where the physical media of the hard drive is and the mechanical guts behind it, or the electronic guts behind it that are interfacing those two, right? Stuff can go south there. And in that case, you're not really any better off than you are with the mechanical drive. But these hybrid drives, they're half man, half machine. Or in hard drive speak, they're half crap, half good. Half crap, half awesome. Something like that. What are we going to put on the solid state portion of our hard drive? And then what are we going to put on the mechanical portion of that hard drive? What's appropriate to put on the solid state portion? Operating system. Because only part of that operating system loads into memory when you first launch the operating system. A minimal amount of that operating system is going to get loaded into RAM. Because operating systems are big. And then new aspects of the operating system will get launched as needed. So let's say you plug in a new device. Now the operating system may have generic support for that device. That aspect of that driver, they're called drivers, and we'll talk about the driver subsystem of operating systems, that gets loaded into memory on demand. Well, if the operating system is the piece of software that sits between us and the hardware, it would be advantageous for us to have all that crap happen fast, right? So maybe we put the operating system on the solid state. What else? Could we generically say any application that's going to be loading stuff into memory very often would make a lot of sense to have it on your solid state drive? Like video games. And if you play a lot of PC games, those games are constantly reading and writing. It would be very much advantageous to have those on the solid state drive. Anything else you might put on the solid state drive? You might say if you have the space, maybe applications you'd use often. Just because of that 1 second or 2 second launch time difference, something like that. If you have the space. Similarly, would it make sense for the operating system to do all the virtual memory using the solid state drive versus the mechanical drive? So now swapping between fake memory and real memory happens even more quickly, right? So do fusion drives make sense? You can go out and get a fusion drive. That's kind of Apple's name for it. Hybrid is everybody else's name for it. It's the same crap. You can go out and get one of these, and you can get like a 3 terabyte drive. Maybe it has 128 gigabytes of solid state, and the rest of it is mechanical. And we're okay with that. What are the types of things we want to put on the mechanical side? What's okay to put on the mechanical side? Yeah, the illegal movie. That's good. All of our music. That's good. Stuff that doesn't need to be fast. Stuff that we're not relying on as an experience. When we double click on an MP3 and it starts playing, if it starts playing, in a quarter of a second less time than it would take to play on the solid state, we don't necessarily care. So we got 3 minutes to wait until we need to load the next song. And realistically, iTunes or whatever music player you're going to use is probably going to load the next song up before the previous one ends. So you're not even going to realize the delay. So mass storage stuff on your mechanical drive and fast storage stuff on the solid state drive. So when we talk about storage hierarchies, the different types of storage inside of our computers, there's 3 things to consider: speed, cost, and volatility. The more volatile, typically the shorter term it's made to store stuff, typically the faster it is, and typically the more it costs. The low cost stuff is probably going to be slower, bigger, and less volatile. Hard drives. 3 terabytes for $140, $150, whatever they cost. That's a very low volatility type of situation. They're meant for long-term storage. We get a whole bunch of crap in there. They're low cost, but it's relatively speaking slow. So we have this idea of caching. So caching is copying information into faster storage systems, maybe temporarily, to make us believe it's happening more quickly while the rest of it's getting copied into slower stuff. And we've seen ideas of caching or buffering in some of our daily applications, or applications we use often. If you watch Netflix and you hit play on a show, how long until that show starts playing? It depends on your internet connection. Sometimes it might be 5 seconds. Sometimes it might be 2 minutes. Because what it's going to do is it's going to start downloading that show into a buffer, which is memory, Because whenever you're watching a movie, that's got to be loaded out of memory. Because it's showing, let's just say, 60 frames a second at, 1080p resolution or whatever it might be, high definition. That's moving a lot of data. And we don't want to be loading that off a hard drive in real time. Because every, quarter of a second, your movie will pause and stutter. And I don't think we'd watch an entire movie with Portuguese subtitles with that experience, right? So we're going to wait for it to finish buffering. And the idea is it gets an idea of how fast your internet connection is and gets far enough ahead that by the time you get to the end of the movie, it's had a chance of downloading the entire thing. And from your perspective, you didn't even notice because it just kept downloading. It cached part of it into memory. Now, when you bought your processors for your computer, for those of you who bought a computer, usually the more expensive processors, there's multiple things in processors that they brag about when you're looking at the specs of them. You have processor speed, right? How many gigahertz is this processor? Then you have the architecture of it. Is this the Core i7? Is this the Core i5? Which revision number is it? Blah, blah, blah. Then they talk about things like L1, L2, L3 cache. We've seen those? Things that have bigger numbers of each of those tend to also cost more. That gets back to the speed cost volatility. L1, L2 cache, L3 cache, these are chunks of memory of varying distances from the actual CPU, the actual brains that's inside that processor. So when you look at this computer processor, you look at this chip, and you think that's all brains. It's not. Only the core, or the multiple cores in that thing, are the actual brain. Surrounding it is a whole bunch of other things. Memory registers, which are hardware variables, and now these additional L1, L2 cache things, which is really, 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 really fast, larger storage size compared to registers. Registers might hold 64 bits of data in a single register. So a very, very tiny, it's literally the size of a variable for a storage container. Super fast, super expensive, relatively speaking to cost per bits, let's say, but really, really fast. L1 cache is an opportunity for us to have something that lives almost as close to the processor as the registers. Gives us a little bit more memory. So it's going to be super, 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 super fast, and we can store more general purpose stuff in it. But because it's so close to the processor, the communication between that memory and the processor will happen, let's just call it nearly instantaneously. Not a very long highway in between the two. Then you have L2 cache. Typically L2 cache has even a little bit bigger size. It's not quite as close to the processor as L1, but it's still quite close. So it's going to also be very fast. Right? Then you have L3 cache. A little bit bigger size. So on and so forth. Kind of makes sense? So, for homework, I want you to write a 2 to 3 page paper comparing and contrasting L1, L2, and L3 cache. What kinds of things are they used for? How do they differ? You can talk about how they impact the price of a processor if you want, but I'm really looking for is the applications of very, very, very fast non-register memory. Registers being those hardware memory buckets. So what is the difference between L1, L2, and L3 cache? Why do we need it? Make sense? Questions, comments, concerns, bribes? I will see everybody on Wednesday.